These are the objectives, expression principle, and terminology used to express partitioning of solute and efficiency of separations. Classify extractants used for metal ions and the role of diluent and modifier in the extraction of metal ions. This particular section focuses on a system where a solute is brought in contact with two immiscible solvents. What will be the constraints limiting the partition of the solute in the two phases? How will be the distribution quantified? Next, bus stop is Trishulya Square. Can the distribution pattern of the solute be evolved into next bus stop is Trishulya Square. A method of separation of the Trishulya Square. This bus stop is Trishulya Square. Square. This bus stop is Trishulya Square. Vartaman bus stop, Trishulya Square.
Sir, are you there?
Hello, sir.
Hello, sir.
Sir, we are not able to see the screen.
Again, good evening to everyone. Am I audible to all? Anyone, please reply.
Yes, sir.
Thank you. So sorry for the inconvenience you all are faced. So let's
Yes, sir.
okay. Let's continue our class with just wait. I'm sharing my screen. This one.
Okay, sir.
Okay, okay. I think my screen is now shared with you all, and we have solvent extraction. We have solvent extraction part. This is our unit 2. I think my slide is very much clear to all, visible to all.
Yes, sir.
Okay, thank you. So today we have the second unit of your paper MCH 002 of PG DSC program. That is your solvent extraction. As we know, if you want to prepare a solution, then we need two ingredients such as solute and solvent, and solvent is the medium in which solute is dissolved to prepare the solution, and the solvent may be a neutral solvent, organic solvent, or an inorganic solvent. The best inorganic solvent is our water. Organic solvent is your benzene or ether, and then so these solvents, that is inorganic solvent and organic solvents, they are how they are extracted, by which methods. So mm, these things we will discuss today in our today's session. So okay, okay, okay. So then slide. Just wait. Okay. So these are the content of today's class. Introduction followed by principle of solvent extraction. Then what is distribution coefficient, distribution ratio between aqueous solvent and organic solvent, relationship between distribution coefficient and distribution ratio, factors affecting solvent extraction, separation factors, then batch extraction, counter current extraction, application, what are the application of these, and then last one will be some numerical problems. Then what is solvent extraction? Solvent extraction is also called as liquid extraction, or this is in a chemical term it is partitioning. That is, it creates a barrier, or in common words it creates a boundary between two different medium solvents, like your aqueous and organic medium, which are very much separated through their difference in their densities. So these two liquids which are gets extracted or separated must be immiscible, that they do not mixed with each other. Immiscible liquids are these are ones that cannot get mixed up together and separate into layers, when shaken together. These liquids are usually water and organic solvents. So as we know, a chemical analysis is usually more than a simple measurement. It is a measurement. The operator mainly take care of three components: the system, the properties, and the instrument. So there are three components on which the measurement of the operator depends. It is system, its property, and the instrument we use for the measurement. Then, what are the objective of this unit? The objective of this unit, that is your solvent extraction one, this will be understanding error and types of error, known the distinction between accuracy and precision, express the final result of a measurement and error and types of errors, then find the proper use of significant figures in measurement of calculation as written in your PDF. Okay, so let's go to our PPT. Solvent extraction is the process in which a compound transfer from one solvent to another owing to the difference in solubility and distribution coefficient between these two immiscible solvents. So solvent extraction, this is a quantitative separation of compounds. This is just a quantitative, not qualitative. When extracting solvents is stirred with solution containing solute and solute, then solute from original solvent gets transferred into an extracting solvent. So this is a very important point in solution extraction point of view, that the solute dissolve in the solvent um, uh, to form the solution, it gets transferred into the extracting solvent by the solute. When stirring is stopped, extracting solvent from separate form a separate layer, and now it contains solute of interest. As compared with other separation methods, it gives a better separation effect than chemical precipitation and a higher degree of selectivity, faster mass transfer than the ion exchange method. So this solvent separation technique is a higher degree of selectivity. Selectivity means we select the solvents phase by phase or one by one. That higher density will separate first, followed by the lesser denser liquids. So this is more effective than your ion exchange method, where cation and anions are used to exchange the ions and to separate the constituents from its mixtures. As compared with distillation, solvent extraction has advantages such as low energy consumption, large production capacity, fast action, easy continuous operation, and ease to automation. I already told these things yesterday, that as compared to your distillation, as compared to your ion exchange and other separation techniques, this solvent extraction or solvent separation method is very much user friendly. It is a low energy consumption, that like your distillation, external heat is required. Like your ion exchange method, ions, external ions are required. But in your solvent extraction or solvent separation process, only a apparatus called as separating funnel is required to separate the solvents on the basis of their densities. This is also large production capacity, fast action, easy continuous operation, and so on. These are the solvent commonly used: ethyl acetate, diethyl ether, dichloromethane. This is chloroform, dissolved in 10% water. So water also dissolve in organic solvents. What are the organic solvents? They are ethyl acetate 3% of water is dissolved. Diethyl ether 1.4, dichloromethane 0.25, then chloroform. The formula is CHCl3 and its percentage is 0.056%. Uses of solvent extraction processes. Solvent extraction is used in the processing of perfumes, vegetable oil, or biodiesel. It is also used to recover plutonium from irradiated nuclear fuel, a process which is usually called nuclear reprocessing. The recovered plutonium can then be reused as nuclear fuel, which are used in the nuclear reactors for nuclear fission and fusion reactions in your nuclear chemistry part, like your preparation of your hydrogen bomb and your atom bomb. These involve nuclear fission and nuclear fission reactions, fusion reaction, which need nuclear fuel. So, how nuclear fuel is recovered from the solvent mixture by these solvent extraction processes. The property of the solvent used for solvent extraction. What are the properties? The solvent should be well miscible with the liquid to be extracted. That which liquid is to be extracted, the solvent should be miscible. The solvent should not be miscible with other component of the mixture or react with the solute. That means the component which you want to separate from the mixture, the solvent we externally added to that mixture must be miscible with that particular component only, not with the other component of the mixture. The boiling point of the solvent should be low enough, that is below the melting point of the solute, such that it cannot be evaporated easily after collection. Then it should have a favorable temperature coefficient. Okay. Then just I read these things. Points to be considered: the solvent should be able to dissolve at least one component to a large extent than the rest of the component in the mixture. The reaction taking place should be stable and irreversible. A reversible reaction, what happened to reversible reaction? If I add a solvent to a mixture and some a definite component is miscible with that solvent, and if the process is reversible, then the component again reverts back to its state, so it cannot be recovered 100%. So that's why the reaction between the solvent and the particular component should be irreversible, not reversible. The compound formed after the reaction should be easily separated from the extracted compound so that it can be reused. This is also an important point, that the compound should be separated and it should be reused. The density of the compound should be different from the required component to the help to help the separation readily. Density must be different. It should be inexpensive and cost effective. The solvent should not be toxic or corrosive, and that is, it cannot harm to the instrument or the person which handle it. Other factors important during solvent extraction are viscosity, boiling point, flammability, etc. This is very much important. Distribution coefficient. So distribution coefficient, what is distribution coefficient? This is the mm, concentration of the organic phase divided by concentration of the aqueous phase. So before going to these things, just see this diagram first. This one. My slides is clearly visible, students.
Sir, can you enlarge your screen?
I think this is the maximum enlargement, and this is it is okay now.
No, sir, your screen is looking too.
Small,
Yes, sir.
but this is the maximum enlargement my laptop permits. So I do not have mm, any extraction option, and I think other student facing the same problem. Anyone?
Yes, sir.
Any? So the screen is somehow small.
Yes, sir. Small.
You are using mobile or laptop?
Mobile,
I
sir.
am using my laptop.
Okay, okay. So in your mobile, you may enlarge your screen by using your fingers. Okay, and in your laptop,
No, sir.
you
Your side mistake is.
my side. Just okay, okay.
Yes,
Wait.
sir.
Yeah, yesterday the screen is okay.
Yes, sir.
Okay, 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 okay. I'm just wait. Is it visible now?
Yes, sir. Now it is okay.
Yes, sir.
Now?
Yeah, it's okay,
Yes, sir.
sir.
Okay, thank you.
Thank you a lot.
Okay. So, just before going to the distribution factor and distribution law, let's go to, just wait. Let's go to, just wait. Yes. So let's go to this figure. This apparatus is known as separating funnel. This is just a conical shaped glass apparatus and used in research labs and your master degree labs, where two solvents are separated through vigorous stirring. Here, the blue color is your water, that is the aqueous phase, and the transparent is your organic phase. That is, the total content here is 0.50 gram. That means it is the mixture of both aqueous and organic layer. Okay. Then if I vigorously shake or shake this one, then what happen? After some time, the two phases get separated with respect to their densities. So the below layer is the aqueous phase and upper layer is the ether or organic phase. So what happened? Now when I open this key of this apparatus, this 0.21 grams of your aqueous layer water first gets separated. So this is in your first conical flux. Then followed by the separation of the second. This is the second one. Okay. Then if the second one, the aqueous layer 0.21 gram, because this is the lower part. If I separate it first, then maybe some ether gets added to this aqueous layer or water. So again, we will put this water or aqueous layer to the separating funnel again. Then again vigorous stirring. Then what happened? This 0.12 grams of ether again separated. Then we have 0.09 gram of water and 0.12 gram of ethereal layer or organic layer. And again, this layer may contain some ether. Again, the same process continues, and at the end, we have 0.04 gram of aqueous layer and 0.05 plus 0.12 plus 0.29 grams of ether layer. So this is the overall idea of your solvent extraction through simple participation method, partition method, by using your separating funnel. So there are two phases, that is aqueous phase and organic phase. So in our, just wait. So in our distribution law, so what distribution law said? First, we will go to that PDF. Then we will have that PPT. Okay. Okay. So now just see these things. We have distribution law. So what this law states? This is otherwise known as Nernst distribution law. So Nernst is the name of the scientist in 1891. Okay. So this law states that It is clear from the above discussion that if the system is composed of two immiscible solvents, immiscible means it may be aqueous or organic phase, and one distributing solute, there is 1 degree of freedom. The ratio of the concentration of the solute in the two phases is invariant. It is independent of the total concentration. So if I have two solvents named numbered 1 and 2, so S1 is equilibrium with S2, then the distribution coefficient Kd will be concentration of S2 divided by concentration of S1. So concentration, it is the strength of the solvent or strength of any liquid or solution. Concentration is expressed in terms of four units. These are the percentage, molarity, normality, and molality. So molarity is your moles per liter, normality is your gram equivalent per liter, and molality is your moles per 1000 gram of solvent. So this is your molality. So the in either concentration term, the concentration of the solvent is expressed, that is concentration of product by concentration of reactant. So that's why it is your S2 by S1, where Kd is the distribution coefficient. This is a constant, or extraction coefficient. It is independent of the total concentration of the solute and the phase volumes. So this is the distribution law. Then we have distribution coefficient Kd. So what is distribution coefficient? Now when a solution is placed in separator funnel or separating funnel and second with an immiscible solvent, solutes from dissolve often dissolve in part in both the layers. The components are said to be partitioned between two layers or distribute themselves between two layers. When the equilibrium has established, the ratio of concentration of solute in each layer is constant for each system, and this can be represented by the value of K, where K or Kd is known as partition coefficient, distribution coefficient, or is your extraction coefficient. The unit of Kd will be, if it is expressed in terms of molarity, that is moles of solute present per liter of solution. So this is moles per liter. So if it is molarity in organic phase by molarity in aqueous phase, that is in our example, it is molarity of ether divided by molarity of water. Uh, so the Kd or distribution coefficient, when a compound is placed in contact with two immiscible liquid, then the compound itself gets distributed in these two liquids. This is an equilibrium process governed by temperature of the system. Let us suppose compound A is to be extracted from aqueous solution into organic liquid. Then for compound A, the equilibrium can be represented by A aqueous is in equilibrium with A organic. Then Kd will be concentration of organic phase of A divided by concentration of aqueous phase of A. So this is the value of Kd. Amount remain extracted from equilibrium coefficient. It is clear that some quantity of the compound will remain unextracted in aqueous phase. In single extraction, quantitative separation of a compound from aqueous phase into organic phase is not possible. Thus, for quantitative extraction of a compound from aqueous phase into organic phase, aqueous phase must be extracted again and again, that is number of times. Just see this one, where aqueous phase is extracted again and again because the solute uh, or the minute part of the solute may dissolve in the aqueous phase. So that's why the aqueous phase gets again separating again and again by adding ether. Okay, so this is the equation, that is your xn equal to xa. Just take one screenshot of this slide. Xn equal to xa v aqueous divided by kd v0 plus v aqueous, where N is the number of times solute is extracted from aqueous phase. Xn is the quantity of the solute. Xn remained in aqueous phase after n extractions. Xa is the millimoles of solute taken in aqueous phase. Xt is the distribution, Kd is the distribution coefficient. V aqueous is the volume of the aqueous phase. VO is the volume in the organic phase. So this is your quantity of the solute remained in aqueous phase after n times of extraction, Xn. So this is one equation which may be applicable in some numericals you may face. Then efficiency of extraction. What is efficiency? If I input 100 calorie of energy to a system, and the system's output is 60 calorie, that means the efficiency of the system is 60%. That is output by input into 100. This is your efficiency. So efficiency of extraction, and efficiency is always expressed in terms of percentage. So that's why it is multiplied by 100. So it is percentage extraction or efficiency of extraction is another term used in solvent extraction to express efficiency of extraction. It can be calculated percentage of E equal to moles extracted divided by mole in aqueous phase into 100. Which mole? It is a mole of the solute, which we have used to extract the solvent. So the mole extracted of the solute divided by total mole present in the aqueous phase into 100. This will be your efficiency. Then separation factor. How we will separate the separation factor. It is denoted by beta. It is your beta. Beta equal to, it is the ratio of your distribution coefficient of the solvent A divided by distribution coefficient of the solvent B. So if this is a factor, that is, the factor means it is dimensionless, it has no dimension. So if the solution to be extracted consists of two solutes A and B, and we have to separate A and B, then we will use extracting solvent which will dissolve more quantity of A and very less quantity of B. Under this condition, effectiveness of separation is expressed in terms of separation coefficient or separation factor. Then it is beta equal to Kd of A divided by Kd of B, where beta is the separation factor. It should be very high to separate to solute by solvent extraction. Otherwise, the clear separation will be very difficult. So, for a better solvent extraction, the value of beta, that is the separation factor, must be high, must have high value. So this is the separation factor, that is the distribution coefficient of solute A divided by distribution of coefficient of the solute B. Then another factor or ratio comes. This is your distribution ratio. So what is distribution ratio? As mentioned here, many substances undergo dissociation in aqueous phase, like weak carboxylic acid such as benzoic acid and phenol. That means in aqueous phase, organic solvents gets dissociated. Under this condition, let us now the benzoic acid Ha is dissociated to give benzoate ion plus H plus. A minus is the benzoate ion. The substance which undergo by accounting dissociation in aqueous layer, the distribution coefficient in modified form can be defined as distribution ratio. So where the distribution ratio is symbolized as capital D, which is equal to your Ha, that is the benzoic acid, divided by your concentration of benzoate ion in aqueous phase plus concentration of the benzoic acid in aqueous phase. In the in the numerator, it is concentration of benzoic acid in organic phase divided by concentration of benzoate ion in aqueous phase plus concentration of benzoic acid in aqueous phase. So let's go to our PDF. You have very good examples in PDF. Just parallelly, I have to show you. This is the distribution ratio, and the formula is total concentration of solute in organic phase divided by total concentration in aqueous phase. Okay. So, for example, we have this one. Just see this one. Concentration is organic phase divided by concentration is aqueous phase, because in aqueous phase the acid will be dissociated to give benzoate ion and acid. Sorry. Yes. So this is the distribution of benzoic acid between benzene and water. Okay. So this is benzoic acid HBZ. It is added in aqueous phase H2O, which liberates H plus ion here to give hydronium ion H3O plus benzoate ion Pz minus. So in the benzene phase, the partial dimerization of benzoic acid takes place. So in a benzene phase means it is the organic phase. So in aqueous phase, benzoate ion is formed. In organic phase, dimerization occur. That two benzene gets dimerizes to give a single molecule, right? So three species will be there. The first one will be your benzoic acid, second will be your benzoate ion, and third will be your dimeric benzoic acid, HBZ twice. So there are three species from these two equilibrium reactions. Then the value of distribution coefficient Kd. So the Kd for your first benzoic acid HBZ means benzoic acid. It is benzoic acid concentration in organic phase divided by benzoic acid concentration in aqueous phase. This is the formula that we learned earlier, that this is a distribution coefficient. So similarly, the distribution coefficient for benzoate ion Bz minus, it will be the concentration of Bz ion in organic phase divided by concentration of Bz ion in aqueous phase. Similarly, the distribution coefficient for the dimeric molecule, the dimer of benzoic acid HBZ twice. This will be the concentration of HBZ twice organic phase divided by HBZ twice in aqueous phase. So O and A represents organic and aqueous phase. Just remember these things. And D equals to, D is the distribution factor or distribution ratio. It is equal to total benzoic in aqueous phase to divided by total benzoic in is so sorry, this is wrongly written here. Total benzoic in organic phase. This must be organic. This is not aqueous. This is organic. Total benzoic in organic phase divided by total benzoic in aqueous phase, because aqueous phase has the higher density, so it is always in the denominator. So that's why total benzoic in aqueous phase divided by total benzoic is organic phase by aqueous phase. So that is equal to D equal to HBZO plus HBZ twice O divided by HBZA plus Bz minus A. Just see here, in organic phase, the dimeric molecule is written. In aqueous phase, the benzoate ion is written, because this is the reaction. Where in aqueous phase, benzoate ion is formed, but in organic or benzene phase, we have dimerization of benzoic acid. Okay. Similarly, if I take another example of osmium tetroxide with between carbon tetrachloride and water. So the solvents are carbon tetrachloride organic solvent and water is the aqueous solvent. And what is the solute? This is osmium tetroxide, that is OSO4. So as we
Sir,
know,
excuse me.
Yes.
Sir, the problem is occurring the same thing previous which has happened. Your screen is invisible, sir.
Invisible.
Too small.
Why these things happen? Just wait. Yesterday, you faced the same problem. Yesterday, everything was okay.
Yeah.
Okay, okay. Just wait. Again, I am sharing my screen. Is it okay now?
Yeah, it is okay, sir, now.
Actually, I do not understand what happened in the mid of our class today. So, okay. So this is the distribution ratio, that is total concentration in organic phase divided by total concentration in aqueous phase. So we have this example. Second example will be our distribution of osmium tetroxide OSO4 in carbon tetrachloride CCl4 and water. Then the reactions are OSO4 will be changed to H2SOSO5. That is, it will reacted with water H2O, 2 molecules of H2O to give H2OSO5. That is the didesic acid. That is um, osmionic acid H2SOSO5. Then H2OSO5 dissociates to give H plus, and this is your HOSO5 minus osmionate ion. Then again, this ion will dissociate to give OSO5 2 minus. This is the reaction is supposed to be happening in aqueous phase. So we have ions. Just see, we have in aqueous phase we have OSO4. This is the first. Then we have here, this is the second H2OSO5. Then we have this one, the third H2OSO5 minus, then OSO5 2 minus. So we have 4 things in aqueous phase. But in organic phase we have tetramerization. This will be OSO4 tetramer will bonded here to form a bigger molecule, that is a single unit, that is OSO4 whole 4. So in your organic phase we have 2 parts, OSO4 and this big molecule, that is OSO4 whole 4. So here the distribution ratio or distribution factor will be total concentration of osmium in organic phase divided by aqueous phase. So in organic phase we have OSO4 and OSO4 4. So these things written here, OSO4 in organic phase plus 4 times OSO4 0. So that means, and it is divided by your aqueous components, that is OSO4, then H2OSO5, HOSO5 minus, then OSO3 O minus, O5 2 minus concentration. Okay. So just go through these things, and next one will be the percentage of extraction. This is very much simple. Percentage means we have 2 things, that is let us F is the fraction of the total metal in the organic solvent at equilibrium. Then if F is the fraction of the total metal present, then 1 minus F will be present in your aqueous phase. The total will be 1. Okay. Organic phase plus aqueous phase equal to 1. That means if in organic phase it is 1 minus F, then in aqueous phase it will be F. So the total metal in organic phase by total metal in aqueous phase will be the metal concentration in organic phase divided by metal concentration in aqueous phase. What is the metal concentration? This is fraction F. Organic phase means it is F by VO divided by 1 minus F by VA. So by simplifying these things, we have F equal to dVO divided by VA plus dVO, and in percentage, that is efficiency, we have 100F will be 100D divided by these things. Okay. So finally, we have percentage of E efficiency equal to 100D by D plus 1, where D plus 1 is the denominator, that is D plus VA by V0. This is taken as 1. The volume of organic phase divided by volume of aqueous phase by organic phase. Let the volume be equal, then this will be 100 D by D plus 1. Okay. So this is just a percentage extraction versus distribution ratio graph. This will be looks like this. Then we have separation factor. Just go to our slide. So factors affecting solvent extraction. The first one is the masking agent. These are chemical species which do not allow to extract unwanted metal ion with metal ion of interest. That means these chemical species marks or entrap the species which are not wanted, that is unwanted metal ions. Then second one is modifier. This will modify. What to modify? These are the substances when added into aqueous phase, they increase the solubility of the solute which is to be extracted into organic solvent. So this modified's role is to increase the solubility of the solute in aqueous phase, which are supposed to be extracted into organic phase. Usually high molecular weight alcohols are used as modifiers in solvent extraction. So if modifier is needed, then generally alcohols are high molecular weight alcohols are generally used, which role is to increase the solubility of the present solute, uh, which are supposed to be extracted in the organic solvent. Then very important factor is the oxidation state. By carry out the redox reaction with a suitable reagent, oxidation state of metal can be changed. Then we have pH factor. This is also another important factor. pH, that is the pH is as we know, pH is the it is a scale to measure the acidity or alkalinity of a particular solution, and pH is range from your 0 to 14. If it is 7, it is neutral. Below 7, it is acidic, and above 7 and below 14, it will be basic or alkaline. So, can anyone tell me what is the difference between base and alkali? What is a base and what is an alkali? Am I say that sodium hydroxide is a base or sodium hydroxide is an alkali? Anyone have any knowledge on this? Alkali and base, because both have a pH greater than 7 and less than 14. If it is a base, the pH is greater than 7, and if it is an alkali, it is also greater than 7. So anyone know that difference between base and alkali? Because this is a common question generally. um, we ask in your practical viva or practical examinations. Okay, so base is something or any compound or any substance which produces OH minus in aqueous medium, right? This is base. What is acid? Which produces H plus ion in aqueous medium. So what is an alkali? Alkali is a base which is dissolved in water. If a base is dissolved in water, then this is known as alkali. So sodium hydroxide is a base as well as it is an alkali. Okay. So if I say alkali, that means it is a base which is dissolved in alkali. Sorry, dissolved in water. So pH is an important factor for the solvent extraction. Then salting effect. The high concentration of salt sometimes help to extract metal ions from aqueous phase to organic phase. Salt increases ionic strength of aqueous phase and thereby increase the solubility of the metal complex into organic phase. This is a salting effect, and this is very much relevant to your common ion effect. So if your salt has common ion to the metal ion present in the aqueous phase, then what happen? The metal ion gets extracted easily by adding external salts. How? We know that the process that is known as salting out of salt. Okay, salting out of salt. That means uh, the salts are added to salt waters like our sea water or ocean water. What happened? The sea water is collected or it is stored in a particular area, and some solid salts are externally added. What happened? The salt dissolved in the sea water gets extracted easily and in very less time. So this process is known as salting out of salt, and this is a phenomenon known as common ion effect. As in our ordinary salt, which we have added externally, it contains Na plus and Cl minus, and the salt present in the salt water, it also the ion Na plus and Cl minus. So what happened? The equilibrium between Na plus and Cl minus in sodium chloride in seawater gets disturbed by increase the concentration of the sodium and chloride ion concentration at the product end. Okay. So what happened? More and more solid NaCl will be formed. So this is just basis of on the basis of your Lee-Chatterjee principle, that is salting effect. Then another one, the synergic agent. Synergic agent, what is synergic agent? Now these are the reagent which when added to organic phase increase the efficiency of extraction. They get associated with metal complex, make it more soluble into organic phase. So synergic effect means that this have your chelating effect. Chelating effect means some ligand is added and this will form a ring like structure, and which is gets precipitated, and we are able to extract the desired component. Okay, so this is synergic agent. Just look at these things. Solvent extraction method of metal ions. So the first one is the chelate formation. What is chelate formation? That means we will have application of chelating ligands. Chelating ligands means these ligands have the property or they have the capacity to form a ring-like structure. Okay, so this ring-like structure is known as chelate formation. Then second one, just excuse me. Okay, the second one is your ion association method, where ions gets associated and we will extract the metal ion present in the solvent. Then solvation method, it is the property of the solvent, that is solvation, that is it is very much similar to your solubility or solution type. Then it is your synergic extraction. Let's discuss one by one. Chelate formation, that is the ring like structure. Okay, so metals form stable and neutral complexes with chelating ligands. This is chelating against, so chelating ligands, like for example, the chelating ligand, the example is ethylene diamine. Ethylene diamine means it has two carbons, double bond is between them, C double bond C, and it is followed by NH2. So this is uh, NH2 CH double bond CH single bond NH2. That means two nitrogens are there, which can donate two lone pair of electron. So ethylene diamine is a bidentate ligand. That means it is one ligand, but it can donate two pair of electrons. So if I if I if I use ethylene diamine two or three numbers, then this will make a ring like structure around the metal ion. And another ring like chelating ligands like your ethylene diamine tetraacetate. In short, it is EDTA. EDTA is a hexadentate ligand. That means one ligand, but it has six donation sites. EDTA, ethylene diamine tetraacetate. So such type of chelating agents or ligands are used to trap the metal or to form the metal a stable complex. So such chelates are usually water soluble. The chelating agents are usually bidentate, which I already discussed. The bidentate ligand is your ethylene diamine ligand, and multidentate, that is your hexadentate ligand EDTA, ethylene diamine tetraacetate ion. These are organic ligands which provide hydrophobic pocket to the metal ion. Okay, hydrophobic means uh, it is hatredness towards water. Hydrophobic. If it is hydrophilic, that means it has love towards water. Phobic means it is hateness. The organic part of such ligands strongly interact with organic solvent, and thereby metachelate becomes soluble into organic phase. That means to soluble the organic metal in organic phase, we have to use organic ligands like your bidentate ethylene diamine ligand or multidentate that is your hexadentate ethylene diamine tetraacetate ligand. Then it is your ion association method, second method. So metal ions form ion complexes with certain ions. In turn, these ion complexes gets associated
Hello,
with.
sir.
Yes,
Sir, can I ask one question, one
yes,
doubt regarding this?
yes,
Sir, the previous chelate formation,
yes.
so are they water soluble or organic phase soluble?
No, these ligands are water soluble, but as we separate the metal ion in the organic phase, so that's why we used these organic bidentate ligands, bidentate or multidentate ligands, because these ligands, as these are organic ligands, so these are soluble in the organic phase, right? So the this is the contrary. I understood your question. This line is the contrary line here, but
Yes, sir.
you have to remember to dissolve the metal ion in the organic phase, we used organic ligands like bidentate ethylene diamine ligand or multidentate, that is hexadentate ligand, that is ethylene diamine tetraacetate ligand, which has six donation sites. Okay.
Okay, sir. Okay.
Also, then we have ion association method, where ion gets associated with the metal ions of oppositely charged. Then we have solvation part. It is the process in which metal ion gets solvated by solvent molecule and trapped inside the solvent cage. Okay, the solvent used for solvation is soluble in organic phase. Hence, metal ion gets extracted from aqueous phase into organic phase. And last one is the example of the mm, things, that is your carboxylic acid, tertiary amine, alkali substituted phosphoric acid. These are can be used as extracts in your solvation process. So solvation process, it is the it will form a solvent cage like structure, and it will trap the metal ion inside the cage. This is known as the solvation. Okay, we can use crown ether. It is a good extract in your solvation process. Then the last one is synergic extraction. So these are the reagent which when added to the organic phase increase the efficiency. They gets associated with metal complex, make it more soluble into organic phase. So this will be your synergic extraction. Then we have solvent extraction techniques, batch extraction, continuous extraction, and counter current extraction. In batch extraction, it is the simplest and most commonly used method, consisting of extracting the solute from one immiscible layer into other by shaking the two layer until equilibrium is attained, after which the layer are allowed to settle before sampling. That means it is just like your separating funnel. That you have to put two immiscible liquids and the extracting solute, and you have to shake it vigorously and settle it down for some time. Then on the with respect to their densities, they will separated. And this is commonly used on in small scale in chemical labs. The most commonly employed apparatus are a separating funnel, as I already mentioned. This is the batch extraction separating funnel. Okay, the batch extraction may also be used with advantages when distribution ratio is large. So when kd, sorry, the value of d, not kd, this is d. When the d value, that is the concentration, total concentration is the organic phase divided by total concentration of the in the aqueous phase. If the ratio value is very large, we may use batch extraction method, that is use of separating funnel to separate the solvents. Then counter current extraction by continuous counter current distribution is the third general type and is used primarily for fractionation processes. The separation through continuous counter current method is achieved by virtue of density difference between the fluid in contact. The same thing, same property or same thing happen here. In vertical column, the denser phase enters the top and flows downward, while the less denser phase enter from the bottom and flows upward. Okay. The choice of method to be employed will depend primarily upon the value of distribution ratio of the solute of interest as well as on the separation factor of the interfering materials. So these are very much depends on the density of the solvents. The higher density will separate first, and the lesser density or lesser dense phase will separate afterward. Then what are the feature of the extrands which are used externally, or foreign substances which are added to the solvent? What are the features? This the extrands must be selective for required metals. That for every metal, the extract is very much selective. The ability to extract the metal, just take one screenshot of this slide for your examination point of view. To be selected for the required metal, the ability to extract the metal at a desired acidity or pH. That means we have to maintain the pH. Then third one will be ease of formation of complex with metal of interest and high solubility of the metal organic species in organic phase. That is similar to your chelating ligand or chelation. Ease of recovery of the metal from the organic phase. Then it must be stable throughout the principal stage of solvent extraction. It is to be prepared in lab in a large scale, because in lab we have to use different amount of extracts in different separations. So that's why large scale of the separation of the extract must be there to have acceptable rates of extraction and stripping. regeneration of extract for recycling in economical large scale process, and there is no emulsion formation. These are the important features of your extracts. So the applications are um, application of solvent extraction, that is determination of iron in a solvent, determination of lead in blood, determination of copper in alloys such as steel, determination of uranium from the minerals, separation of and purification of organic compounds by organic chemist, used in drug industry by analytical chemist, biochemist, and pharmacist. Okay, so thank you. This is all about our PPT. So let's move to our PDF. So these things we already discussed. There is a separation factor beta, that is d1 by d2. I just call these things we have already discussed. They have just remembered in the solvent extraction process in just a general knowledge. We have generally two phases: aqueous phase and organic phase. And basically, aqueous phase has higher density than organic phase. So if I mix two immiscible solvents, one is aqueous phase and another is organic phase, then after vigorous shaking, what happen? And what happen? The organic phase and aqueous phase will be separated. And if the metal ion is present, then we have to use some organic ligands like your bidentate or multidentate ligand to extract the metal present in the solvent. Okay, and there are various factors: distribution factor, distribution law, then then is your separation factor. Then these are the things: multiple extraction with successive portion, like your phase 1 C1 equal to W1 by V1, C2 phase it is equal to W1 W minus W1 by V2, then D will be in phase 2 by phase 1. So these are the things you have to go through, and these are very fundamental things, and you will learn easily. Okay, so in the next part we will have classification of the extraction system, that is it is basically it takes place in three steps: formation of an uncharged complex or extractable species, distribution of the extractable complex or species, interaction of the complex or species with organic phase. These things we already discussed. That is there will be formation of the complex, then distribution of the complex in organic and aqueous phase, then interaction part in the organic phase. Then we have distribution of simple molecule, extraction by compound formation, then extraction by salvation, extraction by ion pair formation. Already these things we will already discuss in our PPT presentation. Distribution of simple molecule like germanium tetrachloride, mercury dibromide, arsenic tribromide, these things. So these are the extraction compound formation method. The steps are more or less same, and this is the extraction by chelating agents like your ethylene diamine bidentate ligand or by using multidentate ligand. Then extraction by organophosphorus esters. This is or organic compounds. So extraction by carboxylic acid and sulfonic acid. So there are examples as well as different processes which depends on different factors like your acidity, alkalinity, then your solubility. These are the factors which are very much effective in your estimation. Okay, so this is acidic organic organophosphorus compound reaction where the M, that is metal M plus oxidation state in aqueous phase, is reacts with M. This is the extract. Okay, M, that is number of mole. M HX is the extract, twice O stands for organic phase. It will give like this product, and depending upon the product formed or the metal ion complex in the organic phase, we will separate the metal in the organic phase. Then we will have carboxylic and sulfonic acid. This is another example. Just go through these things and just see the percentage of product. In carboxylic acid, we will have this compound 56%, where this is 27%. This carboxylic acid group is at the terminal end. This is 56%, but when it is in the middle carbon, it is 27%. So these are the things. This is naphthenic acid. This is another example. Then extraction by solvation. This is already we have discussed. Just we have the simple examples like cerium to tetranitrate and ether, nitric acid. This is TPP. This is, I think, TPP is tri-N-butyl phosphate, and these things are used in your solvation step. Okay. So in solvation, the reagent containing oxygen bonded to carbon such as ester, ether, alcohol, and ketone are used. Reagent containing oxygen and sulfur bonded to phosphorus, these are also used in your solvation step. For example, extract containing carbon oxygen bond. So but these are, just go through these things. These are very much simple things. Okay. uh, these are just examples. Extraction containing phosphorus oxygen bond, these are the structures of your phosphorus oxygen bond, and these esters are used as extract, and this is the example. This is extract. Then this is RO3P double bond O, the example trialkyl phosphate. Then will you have tri and butyl phosphate, and so on. Then we have extension by ion pair formation, ion exchange. This is the example, that is R3N, that is trialkyl amine in organic phase in acidic medium, and A minus, this is a ion, A minus external ion from salt, that is in aqueous phase. We will get a salt formation here, that is NH plus and A minus. This is will be in the organic layer, because this inorganic part becomes organic part when added or reacted with a trialkyl amine. Then this salt will be added to B, and where the A minus becomes exchanged, and this will be anion exchange. So through this process also we can separate the solvents, that will be your ion pair exchange, or this example is your anion exchange process. Then just remember these things. In anion exchange resin, this is the order of preference, that is chloride has the more efficiency of ion exchange than nitrate, followed by your bisulfate and fluoride. Okay. And this is popularly known as liquid anion exchanger. These things, where anion exchange is supposed to be happen. Okay. So then extraction by crown ether. So you see the structure of crown ether here first. I just show you what is crown ether. This is just like a ring like structure, just like this. See this thing. This is known as crown ether. This is known as 15 crown 5. That means here the total number of molecules, total number of atom is 15, and 5 oxygens are here. So the name of this crown is 15 crown 5. Similarly, this is 18 crown 6. So this type of molecules are used to entrap the metal ion from the solvent, and this is a very good extract which is used in our solvent extraction process. that is extraction by crown ether. Okay, these ligands generally contain oxygen, nitrogen, and sulfur. These are the donor atoms, and there will be a cyclic like compound which contains CH2O CH2 bond, just like this. You see this one, CH2O CH2 bond, and this will be continuous to form a cyclic like structure, and this molecule is used to entrap the metal ion present in the solvent. So next will be our diluent and modifiers. Already we have discussed what are the modifiers, and diluent means it will dilute. So what are the regions? Now they are mainly used to decrease the viscosity. The diluent will be decrease the viscosity. Then depending upon the metal to be loaded, an appropriate concentration of the extract is to be used. Thus the diluent provides the solvent for preparing the solution. Preparing the solution of the extract of the desired concentration. Another role of diluent is to decrease the emulsion formation tendencies. Okay, a number of extract are surface active agents and have high concentration. Just go through these things. These are very much simple things. Then we have modifiers. This is already I have discussed. Then this will be your unit 2. Then it is followed by your unit 3. The same things here, but it is the second part of your solvent extraction, where we have factors, as we already discussed, that is factor of pH, molarity of acid, metal ion concentration, presence of salting out of salt, presence of masking agents, concentration of the extract, nature of the diluent. These things we have already discussed. I have just scrolled down the PDF. What are the important parts? In this unit, we have the objectives. We will explain the extraction of metal ion with some important class of extracts. We will enumerate different aqueous and organic phase parameters which affect the extraction of metal ions. Describe various approaches which are generally adopted for metal ion separation, and decide the criteria for selection of the organic phase, particularly for commercial point of view. Then we have extraction by metal chelates, extraction by solvation, extraction by ion pair formation, and extraction due to synergy. Then first one, the chelate ring is just like this. Oxine. This is a organic ligand, or this is its common name is oxine, but its IPSC name is 8-quinoline. 8-quinolinol. Okay, that is 8-hydroxyquinoline. So here what happened? The metal ion react with the hydroxyquinoline or oxine to form a complex ion like this, and liberation of H plus ion, and the dithiazone. This is another ligand which is diphenyl thiocarbazone, popularly known as dithiazone, which is also a chelating ligand, which form a ring-like structure with the metal ion. And metals like manganese, iron, cobalt, nickel, copper, zinc, silver, cadmium, tin, and lead. These things are very much forming chelating compounds with this oxine or dithiazone ligand. Then these are the reactions in aqueous phase and organic phase, and this is the distribution coefficient. Always remember, the organic part is the numerator and aqueous part is the denominator. Do not write the opposite thing. Okay, do not make any mistake. Just remember, organic always in the upper part, and aqueous always in the lower part, because organic has the lower density and aqueous has the higher density. Higher density will be separated first, followed by the organic part. Okay, so always organic will be in the numerator and aqueous will be in the denominator. Okay. Then we have these are the examples. Then what are the conclusions? In order to have greater extraction, the Kf should be large as possible, and just go through these things. Okay. Next we have already we have discussed these things. E equal to 100 d by d plus 1. In our PPT we have already discussed. And extraction by solvation. This is extract with oxygen bonded to carbon such as ether, alcohol and ketone. Extract with oxygen or sulfur bonded to phosphorus such as alkyl phosphates or alkyl thiophates. Then formation of your iron tetrachloroanion in the aqueous phase, like your hexa aqua iron 3 plus reacts with chlorine to liberate one water molecule, and the chloride will be entrapped or will be inside the complex ion Cl, and the charge, that is 3 plus, change to 2 plus. Again the 2 plus change to 1 plus, and there will be 2 chloride ion and 4 water molecule. Then 1 plus change to 0, then 3 chlorine, 3 water. Then we have another chloride, then this will be 0 to minus 1. So this will be water twice. So Fe water twice, Cl4 minus plus water. So for these things the equilibrium constant are K1, K2, K3 and K4. So for the different steps combiningly the overall reaction will be Fe water 6 3 plus for 4 Cl minus. These are the equilibrium constant of every step, and the product will be Fe water twice 4 chlorine minus plus 4 water. So what is the effective equilibrium constant or final equilibrium constant? This will be concentration of this complex, this one, multiplied by water concentration to the power 4, because in equilibrium expression the coefficient becomes the power. So it is 4, the coefficient is 4, so it becomes the power, divided by, it is FeH2O whole 6 3 plus concentration into Cl minus concentration to the power 4. So this is the formation of FeCl4 minus ion. This is ion exchange. Okay. Similarly, formation of solvate using a ether. We will also use ether. So if I put 2 ether here, then 2 water will be liberated. Then we have this equilibrium, the formation of expected complex like this, distribution of the reagent and complex. Then we have polymerization of ion pair in the ether phase. Just go through these things. Always organic layer is above and aqueous layer is below, and always in the equilibrium expression product will be the numerator and reactant will be the denominator. Just remember these things, do not mistake. Product will be the numerator and reactant will be the denominator. Okay. And always put every component of the organic as well as the aqueous phase separately by your square bracket. Square bracket indicates the concentration, that is moles per liter. Okay. So write these things properly in your examination, and just remember 1 to 2 examples for your examination, which is more than enough for your theory examination. Then we will have extraction by ion pair formation. Again the same thing here. Here ion pair will be formed. Then the same thing, what is K? Now it is this ion divided by this. Then it is the reacts with the manganate ion, MnO4 minus. This is reaction with, this is the dissociation. Second step is the association of the manganate ion. Then the distribution. Distribution is total ion in organic phase divided by total ion in aqueous phase. Similarly, this is another example. Just go through these things. This is again extraction of anion metal complex by higher molecular weight amines. So higher molecular weight amines means, just remember this example, trialkyl amine R3N. Okay, this is used for the extraction of anion metal complex. So these are the examples. Then it is your next will be your extraction by synergism. So this will be your which will increase the solubility. So this is your metal ion which added with this type of agent to form the to liberate H plus ion and the salt like things. So here HTTA, that is your uh, and tri-N-butyl phosphate TBP. What is HTTA? Just wait, I am searching HTTA. Yes, this is okay. This is I think one I is not here, so that's why this is thionyl trifluoroacetate. Okay, this is HTTA. I will clarify this you later, okay? Because in online there will be no HTTA here. Okay, we will have. Okay, then another thing, that is tri-N-butyl phosphate (TBP). So these two are used. Okay, this is HA and B is your TBP. So just try to remember 1 to 2 examples, not more than that. Okay, we'll have confusion. Then these are the equations. Then we will have different system factor affecting, already discussed. This is the pH factor, and this is the percentage of E versus equilibrium pH. How the pH with change in pH, the efficiency increases, right? So this is for a particular metal, like your mercury 2. If it is 0, the efficiency is 0. If the pH gradually increases, that is acidity increases, the efficiency also increases, right? So these things you have to analyze. And this is extraction of iron, copper, zinc, nickel, cobalt with Versatic 9 extract. This is the effect of pH with your percentage of E. This is your extraction of some metal by DEHPA from sulfate solution. Then again the same equation here. This is the pH equation. As we know, pH equal to minus log H plus N concentration, but here the equilibrium or the distribution coefficient is highlighted here. Then it depends on the molarity or concentration of the acid. This is another factor. Just go through these things, okay? And these are the symbols of different ions, metal ions. And this circle is for your titanium 4. This square is for your vanadium 4, just like this, okay? So with change in concentration of the acid, how the efficiency the how the efficiency changes. This graph highlights. Then is your logarithm concentration of HCl with percentage of E, logarithm concentration of HCl with percentage E of different extracts. Just do not try to remember these things, okay? This will not helpful in your examination point of view. Just these are in your PDF. Just mm, overlook these things. Effect of metal ion concentration. So if the concentration of the metal ion is more than the solvation of more salt. Then percent of salting out agents like your salting out of salt. That is the external agents are used, that the extracts are added with some common ions, which is effective to extract the metal ion. Presence of masking agents like your crown ether, then some extracts having the like your chelating ligand. These are also the masking agents which creates a cage like structure where the metal is entrapted and it is somehow separated. Okay. Then also concentration of the extract, this is also very much important. That is for a particular metal, what concentration is needed to separate the metal ion or the metal. Then this is log of alamine versus log D. Just overlook these things. This is not needed for your examination. Okay. Nature of diluent, this is also important. Then different approaches for metal ion separation. This is stripping. Then pH of the aqueous solution. Then acidity or molarity, presence of masking agent, selecting, stripping. These are all just repetition again and again. Okay, the same thing is there. Just you have to thoroughly just read this PDF, as well as I will share my PPT with you at the end of this paper. Just go through my PPT and also your PDF. Yeah, I think you will have a good knowledge on these techniques of solvent extraction. Then these are some datas. You do not have to remember these things. This is not needed. Then what are the diluent? What is the separation factor? Uh, just look at these things. Okay. Presence of masking agent in aqueous phase. Selecting stripping from the organic phase. Then criteria for choice of organic phase. What are the criteria? The component of the organic phase should be immiscible. This is a must criteria for your separation. It should have a good stability. A difference in densities of the contacting phase is essential. It should be of great should be as great as possible. Low power requirement of pumping or agitating is required. The interfacial tension should be high for rapid coalescence. The solvent should cause no corrosion. The solvent should have low toxicity. It should have high metal loading capacity. It should be easily stripped of the loaded metal. The extract should have high extraction and regeneration power. The extract should be selective to extract one component of the solution. It should have good kinetic or kinetics of extractions. It should be relatively inexpensive, that is economic. The extract should be highly soluble in aliphatic and aromatic hydrocarbons. So, in this paper MCH-002, you will get very few questions from this part, Unit 2 and Unit 3, solvent extraction. So you will have you should only remember the distribution law, distribution factor, separation factor, and distribution coefficient, these things. And what are the methods like your masking, ion exchange, solvation, chelating. These are the four methods which are used for the separation of the metal ion from the solvent, and the factors which are affecting the solvent separation, as well as the criteria. What are the criteria for selection of your organic phase, as well as your aqueous phase. And I think this is all about your solvent extraction, Unit 2 and Unit 3. And the next class we will have Unit 4, and this is very much interesting, that is chromatography. Okay, our next class will be on when is your next class? It is on 31st of July. I think this is Monday. So 31st of July we will have unit 4. Okay, general principle of chromatography, and I have already prepared one. I think one. Yes, PowerPoint presentation for you also. Basic chromatography technique. We will discuss these things in our later part, in our 31st July class. Okay. So, is there any question related to today's class or anything else, or any question from yesterday class? If any doubt, you may ask, or we may wind up the session. Anil Kumar, Chandini Sahu, then Mahadev Mondol. Okay. So if no questions are there, then thank you to all for and also I kept you all waiting for 15 to 20 minutes to start the class. So sorry for that. And in on 31st July we will have class on sharp 5:30 or 5:30 p.m. So thank you to all. Have a good day, and bye bye.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.